Moore's law is a fascinating principle that predicts the number of transistors on a microchip doubles approximately every 2 years. This means our devices get faster and more powerful without increasing in size. Think about it. The smartphone in your pocket has more computing power than the computers used for the Apollo moon landing. This exponential growth has driven innovation, making technology more accessible and affordable. However, as we approach physical limits of miniaturization, the question arises, can this trend continue? The future of computing might rely on new materials or architectures, but for now, Moore's law remains a cornerstone of our tech evolution.
Boyle's law is a fundamental principle in physics that describes how gases behave under pressure. Simply put, it states that when the pressure of a gas increases, its volume decreases as long as the temperature stays constant. Imagine squeezing a balloon. As you apply pressure, the balloon shrinks. This relationship is expressed mathematically as P1V1 equals P2V2, where P is pressure and V is volume. It's fascinating because it helps us understand everything from how our lungs work to how engines operate. So next time you pop a balloon, remember, you're witnessing Boyle's law in action.
Pascal's law states that when pressure is applied to a confined fluid, that pressure is transmitted equally in all directions. Imagine a balloon. When you squeeze it, the air inside pushes back evenly, no matter where you apply the pressure. This principle is why hydraulic systems work so well. Think of a car lift. A small force applied to a tiny piston can lift a massive vehicle because the pressure is distributed throughout the fluid. It's all about balance and efficiency, showing us how we can amplify force using simple physics. So, next time you see a hydraulic machine, remember, it's all thanks to Pascal's genius. Newton's first law states that an object in motion stays in motion, and an object at rest stays at rest, unless acted upon by an external force. Think of it like a soccer ball. It won't move until you kick it. The second law tells us that force equals mass times acceleration. So, if you push a shopping cart, the harder you push, the faster it goes. Finally, the third law says for every action, there's an equal and opposite reaction. When you jump off a small boat, you push the boat backward as you leap forward. These laws explain everything from why we walk to how rockets launch into space.
Factorials are fascinating. When we say n factorial, written as n, we mean multiplying all whole numbers from n down to 1. For example, 5 equals 5 times 4 times 3 times 2 times 1, which equals 120. It's like a countdown of multiplications. Faktorialsgroß super fast 10 is already 3,628,800. They're used in combinations and permutations, helping us figure out how to arrange things. So, next time you see a factorial, remember it's not just a number, it's a powerful tool for counting possibilities.
Calculus is everywhere in our daily lives. Think about how engineers design roller coasters. They use calculus to calculate the curves and slopes for the perfect thrill. In medicine, it helps model the spread of diseases, allowing us to predict outbreaks and save lives. Even in finance, calculus is crucial for optimizing investments and understanding risk. And let's not forget about physics. Calculus explains how objects move and interact. So, whether you're calculating the area under a curve or predicting future trends, calculus is the tool that makes sense of the world around us.
Pi, the mysterious number that represents the ratio of a circle's circumference to its diameter, has fascinated mathematicians for centuries. It's approximately 3.14, but it's actually an infinite, non-repeating decimal. The ancient Babylonians estimated pi as 3.125, while the Egyptians used 3.16. Fast forward to Archimedes, who cleverly inscribed and circumscribed polygons around circles to calculate pi more accurately, landing around 3.14. Today, we use computers to calculate pi to trillions of digits. Beyond math, pi pops up in nature, art, and even music. It's a reminder that some mysteries, like the universe itself, are beautifully infinite. The Fibonacci spiral is a stunning example of nature's mathematical artistry. It starts with the Fibonacci sequence, where each number is the sum of the two before it. This pattern manifests in everything from the arrangement of leaves on a stem to the swirling shells of snails. You can even see it in the way galaxies spiral in the cosmos. This spiral creates efficiency in growth and energy distribution, allowing plants to maximize sunlight and nutrients. It's fascinating how this simple sequence shapes the beauty and functionality of life all around us, reminding us that math is truly woven into the fabric of nature.